In this work, we present an efficient physics-based method for reconstructing human motions from monocular videos. Our method shows improved overall reconstruction performance and significantly reduced runtime than previous methods. Motion reconstruction from monocular videos is a challenging problem because of self-occlusion, unknown camera parameters, and real-scale uncertainty. Previous results often show artifacts such as foot sliding, jittering, and body floating due to the lack of physical reasoning. To overcome these limitations, we present an efficient gradient-based method for reconstructing complex human motions with physical constraints. Our approach reformulates human motion dynamics through a differentiable physical consistency loss within an augmented search space. This enables us to transform the motion reconstruction task into a single-level trajectory optimization problem. Existing physics-based methods either simplify the problem to focus only on foot-ground contacts and test only in laboratory conditions, or they reconstruct full-body contacts within a standard physics simulator, such as bullet or musical. But reconstructing motions in simulator leads to a nested optimization problem, which is time-consuming. This is the overview of our framework. Given a video clip, we first use a visual model to extract 3D keypoints in Cartesian space. According to our experiments, an improper ground location leads to a large reconstruction error and unrealistic motion. We propose to compensate for the ground plane location through a virtual camera pose variable and jointly optimize with the human pose during the reconstruction. The motion is then reconstructed by minimizing a combined loss function, which includes kinematic loss and physical consistency loss. We adjust the relative pose between the estimated trajectory and the ground plane through a virtual camera transform variable. We construct the landmark retargeting loss to minimize the distance between the reconstructed trajectory and the visual detections. In our work, this term is composed of joint position, velocity, and bone direction loss. We also propose two different terms to solve the rigid body dynamics. First, we solve the joint forces and torques for each individual link, which can reduce the impact during motions like a human would do in real life, and a whole body inverse dynamic, which assumes no joint force limit to guide the convergence. Experiments show that the second term could accelerate the convergence during the optimization. To achieve an even faster convergence, we use different weighted combinations of the loss function during the optimization. Initially, the solver focuses on the kinematic goals and subsequently incorporates regularization, contacts, and rigid dynamics. We minimize the composed loss using a Gaussian-Newton method. Experimental results show that our method can reconstruct acrobatic human motions in just a few minutes, which is more efficient than previous methods. This video shows the reconstruction process of a backflip motion. We can observe the gradual improvement through the optimization results of different iterations. Our method can reconstruct acrobatic motions like a front flip, spin kick, and cartwheel. We can observe obvious visual prediction errors like jittering, sliding, and depth estimation error. Our method can still obtain clean and physically reasonable trajectories after the optimization. We give several reconstruction examples to show how our method improves physical consistency based on the visual predictions. Left and middle videos shows the input and visual predictions respectively. Our method successfully removes the foot sliding, body floating, and jittering from the visual predictions. The main contributions of this work include 3 points. We reformulate human motion dynamics with a physical consistency loss and transform motion reconstruction task into a single-level trajectory optimization problem. We propose to constrain joint forces, torques, reducing joint impacts like a human would do in real life. We optimize the ground plane pose to compensate the camera pose uncertainty during the physical inference to improve the overall reconstruction performance. We also propose several promising directions for future work. For example, we can jointly reconstruct environment features and camera trajectory for motion reconstruction under a dynamic camera. Currently, our method can only be used offline. Real-time reconstruction for character control and the integration with a game engine is a promising application. We also plan to explore the motion reconstruction with more environment and object interactions. Thank you for your attention. Feel free to make contact with us if you are interested in our work.